In today's episode, we are going to be talking about additive categories and categories with byproducts. So, why are we talking about these things? Well, there's a couple ways to motivate this in our series. So, one is that in general, the point of the series is that I want to better understand categories of modules and categorical facts about these things, right? So the category of modules is sort of the quintessential, and we'll really drive that point home probably at some point in the series, but it's really the quintessential example of an abelian category. And there's a theorem that essentially says that, abelian categories tend to look like our module categories. Okay, there's a way to make this precise, Freyd-Mitchell and embedding theorem. So that's, therefore probably a term that we want to understand, right? What is an abelian category? And an abelian category, among other things, there's more to it than just this. But an abelian category has byproducts, and it is also additive. So I'm going to explain those words in a moment. I'll explain it now, and then I'll talk about the second motivation here. So byproducts, I'll give a more rigorous definition in a second, but basically those are things that are simultaneously products and coproducts. So, for example, the direct sum of modules, maybe you've encountered this before, maybe not, but it satisfies both the universal property of product and coproduct simultaneously. So they're one and the same in any category of modules. To say that it's additive means that there is that every Hom set has the structure of an abelian group, right? So certainly in the case of modules, the sum of two maps just, you just take the pointwise sums of those maps in the modules, right? And it also has the property that it respects, it distributes over the composition, right? Okay, so motivation number one, we want to understand module categories better. Module categories are an example of what's more generally called an abelian category, and two of the important parts of that definition are having byproducts and it being additive. So naturally, we want to study those things. Why else are we interested? So more specifically, remember that we're on this journey to show that in the case of commutative rings, so of course we know for commutative rings, if R and S are isomorphic, of course their module categories must be equivalent. I don't think we've actually proved that yet in detail, but hopefully that part is super believable, not too hard to see. What we're trying to show, though, is the converse direction, which again is not true in general, but it's true for commutative rings. And the way in which we're doing this is we defined this thing called the center of the category, and we noticed that so if this ring is commutative, it's its own center, and we noticed that there was an isomorphism in the case of the category of R modules of the center of the category with the center of the ring, right? And we also know, we've also built up some general theory that says, well, if you have an equivalence of categories, because the center is a categorical concept, that should give you an isomorphism of the center of the categories, right? And so we could wind that back in order to recover, our isomorphism of rings, right? By going around this way. The trouble is, all we've managed to show so far in terms of this isomorphism coming from the center of categories is that if you have an equivalence of categories, it induces on the centers of those categories an isomorphism of monoids, right? But what we really need here to conclude that R and S are isomorphic as rings is we need this morphism down here to be a ring isomorphism, right? At the moment, it's really just saying that like the monoid of multiplication of both of these rings is equivalent. So how do we upgrade this? We have an equivalence of categories. How are we going to upgrade this to show that it respects that addition operation? So that is where the additive category is coming into play here, because we're basically going to show that it has something to do with being an additive category. And what is that exactly? Well, it turns out that if you have an additive category, so the way I've defined it here, it seems like it's an extra structure on top of your category, right? But like I've said, all of your HOM sets come equipped with this, abelian group structure. But it turns out that if you have biproducts, which we do in our module category, you can actually use biproducts to define an additive structure in your category. So somehow it's like internal to your category. And then moreover, it turns out that if you're an additive category with biproducts, actually there's only one way to do it. So it turns out any additive structure you could have put on that category that may have seemed external, like sort of this way, this sort of direct way we have of defining addition in the module category, can actually be done totally internally in terms of maps in your category. And so what's the upshot of that? Well, an equivalence of categories should preserve categorical information, right? So that means then that once we establish that the additive nature of a category can be defined entirely categorical, we can conclude that this map between the centers of these categories, or if f, say, is a functor realizing this equivalence, that f is going to preserve the additivity in both of these categories, right? So that is the whole upshot of that. So that is our second motivation, more direct to our specific goal at hand. Okay. So with all of that motivation out of the way, we're now going to turn to the task at hand. So in general, so we say a category has all finite biproducts if for every collection of objects, if we have a collection of objects, there is a product. There is what I'm going to call a biproduct, so I'll call it BP, which is going to be a collection of maps, say I1 through IN and pi1 through pi n, such that the BP, this object BP and all these maps I form a coproduct, and sort of separately BP and all of these maps pi form a product. So in the usual categorical sense. And moreover, this is a critical thing. We're also going to ask that I sub I composed with pi sub I is the identity on AI, and I sub I composed with pi sub J. Sorry, I've done this backwards, haven't I? So sorry, because we include from one of these things, and then we project. So I sub I composed with pi, this will be the identity, and pi composed with ij will be something when I is not equal to j. So to tell you about that something, so we have this extra condition we're also going to put on this in a second, right? So what does it mean to be a biproduct? Well, so we have this object, one of these objects has to exist for every collection, but that should also include the empty collection, right? So normally when we write, say, the universal property of coproducts, right? It's like for every A and B, so that's a collection of size 2, there should be this thing such that for all objects, there's a unique map out of here, right? But now we're going to have the empty collection. So I'm simply, where I would have written A and a B, I'm going to simply write nothing. But I still want there to be some product BP. Even when there's nothing, there should be some BP with the property that there's a unique map out of this into my object. But in other words, what have I just described here? I've said that for every object Z of my category, so I have some object BP such that for every object of my Z of my category, there's a unique map into it. So this is the exact same thing as saying that BP is an initial object in my category. Okay. So fantastic. So conversely, though, remember that BP is a byproduct. So it should simultaneously be true that for any object, now I could call this a different object W, but I'm going to take the same object here, Z, and you'll see why just in a second. For the exact same reasons, but now using product properties, there should be a unique morphism here. So in other words, BP has to be an object which is both terminal and initial. So we call it a zero object. And therefore we have what's called a zero morphism. So the zero morphism is going to be this. And also, if you compose any map with the zero map, you should still get the zero map. Why is that? Because let's say we have some map F from A to B, and we have the zero map. Well, now the zero map, right? The zero map composed with F. This is a map from 0 to B, but remember there was only supposed to be one map from 0 to B. So I suppose I should specify this is 0, the zero map from 0 to A, and this is the zero map from 0 to B. And so it must be the case that the zero map from 0 to A composed with F is the zero map from 0 to B. Okay, but I'm probably going to be sloppy and drop some of my indexing when it comes to the zero map. So just be forewarned. Okay, so now that we know that we have zero maps, I can finally express this other condition, right, to say that this is zero. And you may wonder, why did I go to all that trouble? I should say specifically it's the zero map from A to A. Why did I go to all that trouble? Well, again, remember, we're not assuming ahead of time that we have this additive structure. Of course, we're keeping in our minds the example of the category of modules, but we don't know that we have something like a zero morphism that we can apply to it yet. So that's why I'm making these definitions. Okay, fantastic. So now that we have byproducts, what am I going to do? I am going to try and convince you that just assuming that our category has byproducts, we can define an additive structure. So that's going to be the main goal of today's video. We are not going to finish it because it's going to take some time and some messy details. And I don't want to talk for that long in one sitting today. So two of the main players that we are going to make use of here is called the diagonal and the codiagonal map. So first, let me set up, I suppose, the diagonal map. So I have A. This is a byproduct, and so I've got my projection maps here. Maybe call it something like this, pi to A, and A. Of course, I can put the identity map. Here, and then by the fact that A summed with A is a product, I have there's a unique map making this diagram commute. By the same token, I can take my maps into A plus A because it's a byproduct. And I could put the A over on this side, and again, I could put the identity maps over here. And there, again, because this is supposed to be a coproduct, there should be a unique map making this diagram commute called the codiagonal. Of course, the map is called as such because what does this look like in the category of modules, for example? So if A was an A module, and we know, we have a model for our, biproducts now, in our category of modules, where it would just send an element A to a pair of elements A, comma A. And the codiagonal map will send a pair of elements AB to A plus B, right? So, of course, this is just in the category of modules where we actually have elements. I'm doing all of this in a much more general way. Your category need not have elements for all of this stuff to work. So, moving along, one of the other important players here in this game is going to be the O plus map. So this is not yet actually how we define addition in this category. But again, this is another crucial step. So suppose I have a pair of maps, little a from A to X and little b from B to Y. And what am I going to do? So I'm going to have A direct sum B. So now I have A goes into here, B goes into here. So maybe to introduce some notation, which maybe looks awful, but it's I promise you it's actually going to help us read through some stuff. So this tells us we're including into A, B in that order, and we're including the Bth factor, something like that. I'm going to put X, Y over here. Over here, what I'm going to do is I can apply this map A, right? And then I can include into X, or rather include X into XY. And I can do a very similar thing over here with B, right? I'll apply little b, and then I can include Y into X sum Y. And now, because A sum B is a coproduct, I know that there has to exist a unique map here making this diagram commute called A sum B. I'm going to call that map A sum B. One thing you might be wondering at this point in time, why did I not define this? So I made use of the fact that A sum B was a coproduct, but I also probably could have done this with projection maps instead. I'll leave it to you to try and come up with it. Well, I mean, I'll tell you the answer later in this video. But you could always pause and try for yourself. Why didn't I use the fact that X plus Y is a product? Well, it turns out that these are one and the same. It gives you the same answer. What's really fascinating to me, and maybe someone can correct me on this and find their own explanation, my proof of this that you'll see in this video that we get the same thing actually depends on defining this additive structure first and proving that it has like an identity and satisfies the distributivity axiom. So I think the identity part is something I forgot to mention earlier, but we'll talk about that in a moment. So that's kind of surprising to me that in order to, so I've already made this definition here, and in order to describe more complicated things, or in order to prove certain basic things about it, I have to first invent more complicated structures. Very interesting to me. Okay, so finally we're in a position to define our map. So now I'm going to take little a and little b. These are both going to be maps from A to B because remember, I'm trying to define maps on Hom sets. And I'm going to define my operation. So A sum B is going to be defined as, well, first, so I'm going from A. I'm going to go from A into A sum A, right? So imagine, so this is maybe a bad diagram to have here. So as let me just rewrite another version here. So this would be like A sum A, and maybe I'll call this X just to keep my notation a little more consistent. And this will be X sum X, right? And so I have something like this. So here I would have A sum B would be going here, for example. So I'm first going to take my diagonal map. So I'm going from A, right? I take my diagonal map. I go from A to A plus A. Then I apply my map A sum B, and that's going to take me over to X sum X. And then finally, I apply my co-diagonal map. Maybe I'll draw it here, running out of room, to take me back down to X. And so this A O dot B here is still going to be a map from A to X at the end. And so now here's the main claim of the video. Here's what we're going to start proving today and probably finish whenever I record the next video. We want to prove what? That this has an identity. So there should be some special map such that E sum A is A sum E, which is just A. We want to prove that it is commutative and associative. I'm not going to write it out. I'll just put the word. And we also want to prove that it's distributive. So C composed with A sum B is C composed with A sum C composed with B. Right? Okay. Fantastic. So how do we start doing that? So the first step for us is going to be to prove the identity. I mean, that's the first one. That's the first one on the list, right? So I may as well prove that first. So what are we trying to show? Well, first off, I need to come up with what I think the identity map is. And hopefully, again, you can rely on your intuition with the category of modules. It shouldn't be so surprising to you then that I'm going to claim that the identity is just given by the zero morphism from A to X. So how do I go about proving such a thing? Well, same way we start a lot of proofs, we can unpack definitions, right? So this is codiagonal X composed with A O plus 0 composed with the diagonal map A. And so the trick that I'm going to use here is I'm going to prove sort of an intermediate step that this term just in the middle here is the same as if I did, so if first I projected, that should be an A. If first, so remember, A sum 0, right? This is a map going from A plus A to X plus X, X sum X, right? And so I'm claiming that this would give me the same result as if I had first projected down to A, applied the map little a, and then included into X along the first factor specifically, right? So this is pi1 and this should be I1. And I know I'm going back and forth between the indices being upstairs or downstairs. Hopefully that isn't too confusing. I will probably switch back and forth a few more times. So actually, I think I want to make use of this result in more general terms, though, to be honest. So in fact, if you will indulge me for a moment, so really we care about this in the context of additivity. But I know that later on I'm gonna do a more general result. So what we're actually going to do, we're going to do A sum B and X sum Y. So now I have, so A is going from A to X, and B, this is going to be the 0 map from B to Y. So just to make things a little bit more general, it's going to come up later on. So how can we prove it? How can we prove the equality of these two morphisms? Well, this morphism, remember, was defined by a universal property. So if we can simply argue that this morphism satisfies the exact same universal property, then we're good to go, right? Because that universal property says, oh, there's a unique morphism that does the job. So if we find something else that does the job, it must have been the same morphism all along. Okay, the rest of the video is basically just going to be a lot of me doing that again and again and again. So let's set it up. Let's set up what the universal property looks like for a sum 0. So here we would have I like a b, let's say, and so here's b, and there should be I b a b, and then here we have x and y. Over here, this is going to be a followed by inclusion into x, right? This is just all from our definition. And over here, what we're going to have is the 0 map followed by our inclusion of y into xy. But remember, we already saw that composing with the 0 map gives the 0 map. I think I only argued the composition on one side, but I trust all of you now to be able to carry out the rest of the argument on the other side. So what are we trying to do? So this was the universal, this was the diagram that defined a sum 0. And so I want to try and convince you that I should have given myself more space here, but that this, let me write it bigger, that projecting down to a and then applying little a and then applying the inclusion into the x factor is the same thing as this direct sum, a sum 0. So what do I have to do? I simply need to check that both of these triangles commute here. So all I need to do to prove this is to I'll take my map. Since I already wrote it here, I'll write it here. And I need to precompose, for example, if I want to show the first triangle commutes, I need to precompose with the inclusion of a into ab and see that I get out this map here. Well, remember from our assumption on biproducts, we said that if you include and project, that was supposed to be the identity. And so this part just disappears. It's the identity. And what are we left with? Well, exactly the thing that we wanted to be there. Okay. So now I need to check the commutativity of the other diagram. So I take the exact same thing, I, x, y, composed with a, composed with the projection down to a, and now I'm precomposing with I, b, a, b. But now remember, so this is, I know I'm using slightly different terminology here, but maybe just to help make things a little more clear. Going back, it's these defining conditions, right? So now the inclusion and the pi are mismatched. This is like the case when I is not equal to j. And so we know that this map here has to be 0. But if this map is 0 and we're composing with 0, the whole thing's going to be 0, right? And great, that's exactly what we wanted to show, is that it's this term here. So what does that mean? That means we can conclude that, yes, indeed, this map here is the same thing as a sum 0 because it satisfies the same universal property. And how does that help us? Where was I going? Well, now that we know that, let's see. So a sum 0 was by definition codiagonal x composed with, or sorry, a plus 0, I should say, with our addition operation is a sum 0 composed with these maps. But now this is the codiagonal of x composed with I, x, x, y, composed with a, composed with pi, a, b, composed with the diagonal a. And now I claim that both of these are the identity. Why? Well, if we scroll back up to the maps that defined the diagrams that defined our diagonal and codiagonal, right? That's exactly, these were the defining features, right? If you took the diagonal map and you post-composed with either projection, you would get the identity. And likewise, if you took the codiagonal map and you pre-composed with any inclusion, you would get the identity. So scrolling back down to our argument, where we are in our proof here, both of these terms must be the identity, and so we conclude at last that this is the identity, and that's what we wanted to show, right? We wanted to show that this is the additive identity. Okay, so unsurprisingly, the case that 0 plus A is entirely similar, so I'm not going to do it. And you could say, well, wouldn't it just follow from commutativity later when we prove that? Yes. But if I am remembering correctly, I think somewhere along the lines in this proof, I end up using identity on both sides before we get to commutativity. So what I mean to say is, I'm looking for my water, and I'm not going to pause the video just because I can't find my water. What I mean to say is that actually, I think the proof of commutativity depends on having both the left and right identity worked out ahead of time. And the proof of commutativity also depends on distributivity. So we're going to need to do that one next in the process. So again, I'm just going to do left distributivity for you. You can do right distributivity on your own. Yeah, but both of those, we definitely need both of those in the proof of commutativity anyways. So now I'm going to suppose I have the following setup. A to X. So now A and B are both maps from A to X. And I have a map C that goes here. And what am I trying to prove? I am trying to prove that C composed with A plus B is C composed with A plus C composed with B. Well, again, I can just unpack definitions, right? So this is going to be C composed with the codiagonal into X composed with A sum B, sorry about that, A sum B composed with the diagonal into A. And over here, I will have the codiagonal into Y, right? Because I'm looking at A composed with C. So this is a map from A into Y. So codiagonal into Y of C composed with A, sum C composed with B, and over here I have the diagonal into A. So I need to prove that these are equal. But notice on the very right, I have the same term here. So actually, it would suffice if I were just to show that these two maps are in fact equal. And again, I'm going to use the same trick here. I'm going to show that they lie in the same commutative diagram, and I'm going to exploit some product property here. So in this case, what I'm going to do is I'm going to take A sum A. I'm going to put A's here, and I should say coproduct property. And I'm going to take my inclusions. But this time, what I'm going to do, because I'm showing that these maps, right? These things in red are both maps from A sum A into C. So I'm going to put C all the way over here, and I'm going to put over here C composed with A, and I'm going to put over here C composed with B. And now I'm going to prove, so we know because A plus A is a coproduct, we know that there's a unique map making this diagram commute. And I'm going to prove that both of these two maps in red make this diagram commute. And so by the fact that this is a universal property, by the fact that we know that there's a unique map that has to do the job, if both of these maps do the job, then they must be equal to each other. So Now it's just a bunch of formal checking of details, right? What do I need to do? I need to check the commutativity of both triangles. So first, I'm going to check commutativity up here with respect to this first triangle. So what do I need to do? I need to pre-compose with the inclusion map. So I have C, codiagonal X, A sum B, and I1A, let's call it. Okay. But now, if I look at this first term, right, perhaps I should go up and show you, like, let's recall the diagram that defined A sum B. So A sum B here, so this should be C composed with I, X, 1. Oh, I switched the indices again. Oh, well. Right? It was defined by making this diagram commute. So actually, if I pre-compose A sum B with this inclusion, I should get this. So applying that to the proof at hand, we know that this is C composed with the codiagonal of X, composed with the inclusion, this time the first inclusion into X direct sum X. But now, so I'm not going to go back and forth every time. I've already scrolled up to remind you about the universal property of the codiagonal. I'll let you think about it, or pause, rewind yourself. The universal property here said that if I compose these two things, I get the identity. And so, I made a mistake. I forgot to draw the A. Very important mistake. Yeah. These two things become these two things. Now, when I take these two things in the middle, that is supposed to be the identity. And so, yes, in fact, I do get CA. Likewise, so I'm only going to do so many steps of the proof for you because this video is already going to be very long. But in an entirely similar argument, which I trust you to do now, we can see that we get the other composition here. And so therefore, yes, indeed, this map satisfies the universal property. So, okay, maybe I'll just check the one other side for you. Again, I'll leave this part of the triangle, but now we're going to check that this map satisfies this part of the triangle as well. So it's just the same game. So we've got codiagonal Y, C composed with A, direct sum, C composed with B. We pre-compose with I1A. Now we have to think about, so this one might take a little more thinking because this, remember, gosh, should I draw out the diagram for you? I mean, it'll be A sum A, right, into Y sum Y, right? So the point is, this other map here in the defining condition, this is going to be C composed with A and then post-composed with I1Y in this case, right? So this becomes diagonal Y composed with I1Y composed with C composed with A. But of course, again, this is just supposed to be the identity, and we find that we get C composed with A. Well, wouldn't you know it, that's exactly the thing. Okay, and so I'm not even going to write out the statement of the last one. I'm gonna trust you to do it. So we see that, yes, in fact, both of these maps satisfy the same universal property, so therefore they must be equal. So therefore, these two expressions, of course, if the things in red are equal, then if we pre-compose those with the diagonal map into A, that's still going to be equal. And so therefore, that just came from an unpacking of here. Therefore, we have distributivity. Wow, what a proof, hey? So let's see. Do I want to finish commutativity in today's video? I don't think I'm going to go all the way in today's video, but here's what I will end on. I made this claim that we need to use the theory of, we need to use identity and we need to use distributivity in order for us to show that this map, this A sum B map, that, remember, we defined that. So let me go back up to the definition. So we defined it using the fact that A sum B is a coproduct. And I said that we'll be able to prove that it would have been the same as if we had defined it using like projection maps. And here, this would have been like project down to A and then compose A. And then, likewise over here, and that this should be the same thing whether you defined it using a universal property of products or coproducts. So now we're in shape to prove that. Now that we've developed some things about this this internal addition map. So let's dive into that proof. How are we going to do this? So what do we need to do? We are trying to show that our map, so we have A sum B into X, Y, and here I have X, here I have Y. We're trying to show that it satisfies the universal property of products, right? So this will be pi X, X, Y, pi Y, X, Y. Like I just wrote above, this is going to be the projection from AB down to A, composed with A, and this is going to be the projection from AB down to B, composed with B, right? So we're trying to show this is the universal property of products. We're trying to show that A sum B sits in the middle here, and this is not just for fun. We're going to need this in future videos to carry out some proofs. So what do I need to do? I need to prove that these two diagrams commute. How am I going to do that? Well, I'm going to take A sum B. Oh, I better give myself a little more room. So I need to see what happens if I apply pi X, X, Y after I apply A sum B. But now I'm going to use this result, right, where, we're going to need one more result first before we do that. First, so before we do that, I'm jumping the gun here. This is, of course, something that we're going to have to do at one point. But I'm going to make another claim here. Before we get to that, I'm going to claim that A sum B is A sum the zero map plus 0 sum B, right? Okay, so how do I prove that? Well, again, I said I wasn't going to go up and down and make you guys dizzy, but I lied. So I need to show that the universal property of A sum B is satisfied, right? So I need to check what happens with these pre-composition of inclusions. So let's go ahead and take a look at that. Right, so I just need to show that this thing on the right satisfies the same universal property here. So A sum 0 plus 0 sum B, if I pre-compose that with the sum, with the inclusion into the first factor of A sum A, well, now I've proved distributivity, right? So I know I proved it on the left. I told you I had the proof, on the right is basically the same. So you're just going to distribute this through. We're going to get A plus 0 summed with I1A plus, maybe I'll put, make square parentheses here, plus 0 sum B composed with I1A. And now, by the universal property, the defining feature of this sum, we know that this becomes I1x post-composed with A plus, and this is going to become, now this is I1A, so it's going to be the zero map post-composed with I1x. But that's just the zero map, right? So we've used distributivity, and now we're using that this is the zero map, which makes it the additive identity. So we just get out I1x composed with A, and that's exactly what we expect to get when we precompose A sum B with I1A, right? So just going to show that the universal property is satisfied. Okay, and I will leave it, again, I will leave it to you to check the other side of this, that if you take A sum 0 plus 0 sum B, and you compose with I2A, you get out I2X precomposed with B. So that means that this thing here satisfies the universal property of A plus B, so it's equal. Now we're going to go back, and now we're going to prove that A sum B satisfies the universal property of products. Finally, so A sum B precomposed with projection from xy down to x is, bear with me here. So using this recently obtained result is going to be A sum 0 plus 0 plus B precomposed with pi x xy. And now we can use distributivity. Let me just double check. Is that the way I actually go about this proof? And I got ahead of myself into I got ahead of myself here. Oh, what am I doing? I wrote this on the wrong side. Ay. Crazy. A less lazy man would edit this out. So we project from xy down to x. A sum b. That kind of looks like an alpha. A sum b. So unpacking definitions, get pi x xy of A sum 0 plus 0 sum B. So now I will use distributivity to get pi x xy composed with A sum 0 plus pi x xy summed with, composed with 0 sum y. But now we're going to use another little trick. So A sum 0, we've seen this before, right? So let me scroll up to where we've seen this before. We proved that that had another equivalent form, right? So remember, we proved that it was equal to projecting down to A, applying little a, and then including into the x factor, right? So we did that by showing, so here it is in more legible form, that the universal property was satisfied. So we're going to reuse that little trick here. So reuse that little trick here. So this is now pi projection down to x of, and this is inclusion of x into xy. This is A. This is projection down to A. And now I didn't prove it, of course, but as you can imagine, 0 sum, oh gosh, I call that y. This should be B. I call that y too. Ay. Crazy stuff. As you can imagine, a very similar statement holds over here, right? So this is going to be the same thing, but instead now slightly different. This will be here the inclusion of y into yx composed with b, composed with the projection of ab down to b. So hopefully that's not too surprising. Given the proof of the other fact, I think you'll be able to construct the proof of that. Now, Again, we have an inclusion composed with a projection. That is just supposed to be the identity. Yes, that should just be the identity. So here we get A composed with the projection down to here. Direct sum. So here, now, look, I have a mismatching. So this is, again, the I not equal to j case. So I have a mismatching of the composition. We said that that has to be the zero map. So this whole factor has to be the zero map. But then we're adding 0. So in fact, what we get out is A composed, precomposed with the projection from AB down to A. And let's go and check. Sure enough, that is exactly what we wanted to get by precomposing this thing with this. Okay, so the other triangle I'm going to leave to you, and so that's gonna do it today. So what have we accomplished so far? So we assumed that we had a category. That's a terrible C with byproducts. And I claimed from you, I can't even write, that's not even legible. And I claimed for you that we could define some product, on it that would give it an additive structure, right? So it basically gives a monoid structure to our Hom sets that's compatible with composition. And I've shown that we do have left and right. Of course, I only really proved one side of those, that we do have left and right identities. I did prove that we have distributivity. Again, technically both sides follows from commutativity, but I think we need actually both sides in order to get commutativity. And one of the things that went into this map is this direct sum thing, and we now know that this is defined by either coproducts or products. We can use both of those tools freely. So what's coming up in the next video? Well, in the next video, I'm going to show you a way to rewrite the diagonal and codiagonal maps. We are going to do the proof of commutativity. We're going to do the proof of associativity. And I think there should be enough time to finally, once we put all of those together, then show the uniqueness of additive structure, right? So remember, I made this claim that if you're an additive category with byproducts, in fact, there's no other way to be an additive category except then to, you can't even read this, except to use the structure from byproducts. So we're going to do all of that, I don't know, in a couple weeks. Until then, I don't know, go prove some theorems and QED.